So we start again. Today we have Sergej Moroz, who will speak about two-dimensional Z2 gauge theory coupled to fermion matter from topological order to confinement and fractons. Please.
Yeah, thank you very much for our meeting. And my pleasure to be here to talk about our research. This was done together with my PhD student Umberto Borla, our postdoc Bilahari Evanesan, and my colleague at Technical University Munich, Frank Pohlmann. Okay, so gauge theories pervade contemporary physics. They, are basis of most important theories of 20th century, general theory of relativity, lower, like this. Is it better? Yes. Okay. And also the standard model of particle physics, and gauge principle is a central theme of both these theories, and this allows us to think in a scientific manner about such exotic questions of, for example, what happened just after the Big Bang, or what is the physics next to black holes. And I think everyone who works on gauge theories, at a certain point, should they ask question like, how come that these theories with all their mathematical intricacies and redundancies are so useful to describe like universe around our universe, and if we learn gauge theories in the relativistic context, then the answer one often gets is that this formalism is the right way how to capture three main properties of nature, such as unitarity, locality, and Lorentz invariance. That's all these properties are manifested together in this gauge variant formulation. So condensed matter physics gives a very different perspective on usefulness of gauge theories, in particular in some systems such as fractional quantum Hall, fluids, quantum spin liquids, and also in superconductors. We have some special phenomena. So, for example, excitations are anyons. They are neither bosons nor fermions, but something in between. If we put the systems on closed surfaces with holes, we get robust ground state degeneracy, and also quantum entanglement has very particular pattern. And it turns out that all these quantities are interrelated with each other. They are manifestation of quantum topological order, and gauge theories is the most efficient formalism nowadays to capture these properties and these manifestations of topological order. So this talk will be about interplay between fermions and gauge fields. And so here I show you some examples, famous examples where such interplay happens, such as, for example, half-field Landau level, quantum phase diagram of quantum chromodynamics, so-called Kitaev spin liquids. And so it is my belief that we can learn about this interplay by studying gauge theories with a simple build out of simple ingredients. And for this reason, we kind of decided to investigate the simplest possible gauge theory, which is called Z2 or Eisen gauge theory, which was first introduced 50 years ago by Franz Wegner in the classical setting. And this is arguably the simplest gauge theory which we can define on a lattice. So let me tell you quickly about this gauge theory. So this is some kind of discrete cousin of U1 electromagnetism. So we will be working in 2 dimensions on a square lattice where gauge fields will be living on links. And the simplest Hamiltonian, or maybe, so the degrees of freedom are spin 1/2 degrees of gauge fields, and the correspondence with the electromagnetism, roughly speaking, is shown here. Sigma Z operator corresponds to the Wilson line operator, and sigma X is a phase of the electric field. And the simplest Hamiltonian, which we can write, is shown here. So the first term is just a sum of products of sigma Z on elementary plaquettes, like this. And the coupling I will call J in the following. And then there is a competing term, sigma X, which is related to the electric. This is electric term, and the coupling I will call H. And the special property of this Hamiltonian is that there is it commutes with a extensive number of local generators, which generate the Z2 gauge transformations by acting around every site on such a star. And this kind of breaks the full Hilbert space in a large number of sectors, which can be labeled by eigenvalues of this. And it's customary to, if we do not want to think about any charges, static charges in this problem, we can set all these G's to +1, and this is what is known the even Z2 gauge theory. And what is special about this theory is that it's known that as we tune the dimensionless parameter here, there is a quantum phase transition between the deconfined and confined phases, and these two phases cannot be distinguished with a local order parameter. Already back in 71, Wegener realized that we can distinguish these two phases by studying properties of the loop operators, which we call today Wegener-Wilson loops. And it was realized much later that the more robust way how to distinguish the phases is to study, degeneracies, for example, on a torus. So the manifestation of topological order. So the deconfined phase has Z2 topological order, while confined phase does not and have just a unique ground state. So this is much more robust because this can survive adding matter to the problem. And actually, the first study of the matter added to this gauge theory was done by Fratkin and Schenker, as far as I know, where they coupled Ising matter living on sites to this Z2 gauge theory. So today we'll be talking about coupling fermions to this gauge theory. And so this originated with this paper of Sentil and Fischer, where they started to think what happens if you couple two-component fermion matter to Z2 gauge theory. And recently there was a lot of progress on this problem because people realized that one can do sign problem-free quantum Monte Carlo, and the phase diagram was mapped out. So what happens here is that as we increase the electric coupling, there is a so Z2 gauge field, a special property of it that it mediates a tension between fermions. So this leads to tendency to pairing, and there is a transition from there is a BC, strongly coupled phase, and weakly coupled BCS phase, separated by a quantum phase transition where the Z2 gauge field undergoes confinement, deconfinement transition. Also, at half filling, there is an interesting Dirac deconfined phase, which I will be talking about as well. So people made a lot of progress recently on this problem. And so what we decided to do, we decided to study Z2 gauge theory coupled to single component fermionic matter. So here C correspond to fermions, which carry Z2 charge, and they do not have any spin, so they are spinless. And you see, whenever we hop a fermion from one place to another, there is a oops, yeah, I should better not. There is a they carry with themselves electric strings, which is this blue lines, which just states of the gauge field where sigma X evaluates to -1. So this is ensured by the presence of this sigma Z operator here in the kinetic term. And so now the combined Hamiltonian, the fermionic one, plus the the Z2 Wegener Hamiltonian is invariant under gauge transformations which are modified. So, and it's shown here. So this GR is now multiplied. So this is a star operator multiplied by a local fermionic parity. And so if we want to work, and that's what we do in the sector where there is no static charges, where all Z2 charge is carried by these dynamical red fermions, these red blobs, then the Gauss law gets this kind of this form. So on the bottom, where the star is equal to the local fermion parity. So this is a discrete version of Gauss law. Any questions? Yeah.
The people online, they will see.
Okay, yeah, I can try. It's okay. Yeah, so I'm talking about this Gauss law, this one, yeah. Okay, so this is our problem. So let me also tell you what we are actually doing from the point of view of the fermionic theory. We take a model which has, you know, fermionic parity as a usual unbreakable symmetry, and then we gauge it. And so what is important here is that it's easy to show that if you take your system and put it on a closed surface and multiply all the Gauss laws, then all the sigma x's will cancel, and then you would automatically get that the total fermion parity, which is a product of all you know, local fermion parities, is equal to +1. So secretly, or not secretly, but this model is actually bosonic because we are gauging the fermion parity. And I will show you later much more explicitly how to write it down as a bosonic model. So in addition to this Z2 gauge redundancy, which I told you about, it also has some global actual symmetries. One of them is just U1 symmetry, where we phase rotate the fermions. Also, it is invariant on the time reversal symmetry as well. And compared to the two-component problem, which I told you about before, we are not aware of any sign problem-free quantum Monte Carlo. So it's kind of yeah. So currently, we do not know how to do quantum Monte Carlo for this model. There was a related study of a model on a ladder recently of the same Hamiltonian, but we are trying to understand something about two-dimensional system. So let me ask, I will talk about motivations now, but is there any question about what model we are studying? Anyone?
I have a question. If you, the original Z2 gauge theory, you say that there are two phases, right?
Yeah.
And but if I write the Lagrangian,
yeah,
and I can integrate it out completely, and I only see one phase. So your Hamiltonian is not exactly equal to the origin to the Lagrangian. Not this model, but the first transparency in which you have a Z2 gauge theory.
Yes.
You have two parameters.
Yes, one dimensionless parameter. Yeah. There's one dimensionless parameter which is as I tune
if I take a, not Hamiltonian but the Lagrangian,
yes,
I don't find the two phases.
You should. This is equivalent.
So that was my mistake.
I think either use Lagrangian or Hamiltonian formally. There would be two phases which you cannot distinguish with a local order parameter. Yeah.
But okay, but in the Lagrangian, if I insist on gauge symmetry, there is only one parameter. No? No?
I don't think so, yeah.
Okay, we will discuss later.
Okay.
Okay, sorry.
No worries, yeah. Okay, so why should we be interested in that? So one of the motivation comes from cold atoms. So recently people using some ingenious ideas about Floquet engineering came up with proposals in these two papers here, how to realize it in cold atoms. And there were two experiments, one in Zurich and another in Munich, which prepared like a basic building block where you have two sides where matter can hop and on a link there is a Z2 gauge field. So the hope is now that we can scale it up and create like one-dimensional chains or even two-dimensional lattices. There are more actually ways, proposals how to simulate this theory, because it's the simplest gauge theory one can write. And another motivation actually comes from the Kitaev physics. So it turns out that people realize that you can generalize Kitaev construction to which is originally on a honeycomb lattice with Pauli matrices to kind of gamma matrices, or bigger matrices. And there is a whole family of exactly solvable model. And it turns out that if you take the simplest generalization, this nu equals to 2 generalization, you're dealing with 4x4 gamma matrices, which can be decomposed into the sigma and tau matrices, and you end up with some kind of spin orbital spin liquid. And the funny thing is that, it's in this construction, naturally, this should be happening on a square lattice for nu equals to 2, where after using the Kitaev trick, you have 2 Majoranas per site, which is exactly this single U1 fermion. And so basically, this model is the simplest form of the Z2 gauge theory coupled to U1 matter. So this is another motivation why we are interested. Yeah. Yes, correct. Okay, so in the rest of my talk, I will tell you what we learned so far about this. I will start with 4 limits, where the problem becomes like more tractable. And then I will tell you about how to eliminate gauge redundancy and rewrite this model as a spin model without any constraints. And this we use this to later study it numerically with density matrix renormalization group. So I show you some results which we found. So first about the limits. So the simplest limit I already talked about essentially. So if you decrease the chemical potential, you will you will get 0 fermion filling, and in that case you just have a even Z2 gauge theory. There are no fermions in the problem in the ground state, and so you end up with this phase diagram which I showed you. 2 phases separated by, in this case, Ising criticality, or more precisely Ising star critical point. There is a related limit where you crank up the chemical potential. So you populate all your sites with fermions. Then what happens is that you also end up with a pure Z2 gauge theory, but now on the right-hand side, since at every site you have a fermion, there is a -1. And this is more exotic version of Z2 gauge theory known as the odd Z2 gauge theory. And by now it's also well understood that the phase diagram has also 2 phases, deconfined and confined. But now the phases are more have more structure. So the confined phase necessarily breaks translational symmetry and has this valence bond, forms some kind of valence bond solid. And the topological phase also enriched with some kind of global, enriched with this D8 symmetry. And you also can see that the critical point is not Ising anymore, but it's XY universality class. So this is well understood by now. Yeah, this means that in this theories you cannot have operators which are, for example, Ising star means that there are no operators which are odd under Ising symmetry. It's just operators which are even. So this has to do with the structure. So the way how to get this, say, this critical point here, it goes back to Wegener. So he kind of rewrote the. So you can make a duality transformation to the Ising model, and this is a Ising critical point. But in this gauge theory, you can only have operators which are even under Ising symmetry, and the same here. So like U1, yeah. Bisons become U1 particles in that case, and that's the reason why you have it. Okay, the third limit is also quite simple. Now you can have a finite density of fermions, but you turn off the electric term completely. So this means that you have static gauge fields, and now you just have fermions living in the background. And now, if you want to understand the property of the ground state, it's just a question of energetics, which background is preferred. And one of like at half filling, we can have nice statements about that. So if this magnetic coupling is very small and the hopping dominates, then by the leap theorem, we know that the flux which will be preferred in the ground state is this pi flux. And this pi flux leads to 2 Dirac cones in the fermionic dispersion. On the other hand, if you crank up J, it becomes very expensive to flip plaquettes, and then you end up with just a cosine band. And between these two translational invariant states, there is a kind of transition which is more complicated with progressively increasing flux from one side to another, which was studied in recent papers. I think the most interesting regime limiting case which we can talk about is the case of strong string tension. So imagine that this H coupling is, which is electric coupling, is the largest parameter. Then what happens is that these fermions try to come as much as possible, as close as possible to each other, but because they're spinless, they have to be next to each other, and we start getting this kind of dimers. And these dimers, they cannot sit on top, or they cannot overlap essentially, because otherwise you would have 2 spinless fermions at the same point, which is not allowed. So we have some kind of constrained dimers here. And in order to understand the physics, we can do some kind of perturbation theory. We can first tune the chemical potential of order H to populate finite density in the ground state. And then we do perturbation theory in the hopping and in the magnetic coupling. So what happens is that if I do at first order, the main effect is that it comes from the magnetic term. If I have this kind of fully populated plaquette with fermions, then they have to be connected with the strings, and this magnetic term it kind of hops the strings from vertical to horizontal and vice versa. And this in fact means that this dimer starts to attract each other. And this attraction leads to some kind of clustering phenomena. So mathematically, it's described by first order effect is described by this kinetic term of the famous Roxer-Kivelson model. And now, depending on the feeling, we have, if the lattice is fully filled, it's well known that we would have a valence bond solid with so-called columnar order. While if we have partial filling and there are some, then what I told you about here is that due to this attraction, these dimers will try to cluster into big conglomerates together. So this is the main effect of this term. And we, not surprisingly, these clusters will try to have a small perimeter as possible in such a way that they can resonate as much as possible inside. That's what we checked numerically. So if we go to the second order in perturbation theory, then this hopping term starts to become important. And what I would like to argue is that in this regime, there is some kind of fractonic emergent behavior appearing. This means that if I take a fermion and a long string, so imagine I just try to think now about isolated fermion within this second order perturbation theory, this fermion cannot hop, because whenever it hops, the strings becomes larger, and I go out of my degenerate manifold. So this object in isolation becomes completely static. But on the other hand, if I take dimers, and this is my low energy degrees of freedom, then at second order of perturbation theory, I can hop them, because I first hop this fermion here, for example, towards left, and then consequently also this fermion goes left, and I move the dimer by one link. The interesting thing here is that these dimers, so this effect actually is pretty generic, but what is kind of happening here is that they have some kind of restricted mobility, because while I can hop this dimer horizontally here, I cannot hop this dimer vertically. I cannot move it upwards, because if I would do that, I would end up with a string of length 3, right? So I move this thread upwards, I move this thread upwards as well, and this is out of my degenerate manifold. So they exhibit restricted mobility, these dimers. And in fact, we kind of worked out the full Hamiltonian here, second order of perturbation theory, how these dimers hop. So here is the full Hamiltonian in a pictorial way. And then what we started to do is studied what is the physics of, what is the dispersions which we get. For example, you can take a single dimer and study the dispersion relation. And what we found is that in addition to this dispersing band, which has this small bandwidth, t squared over, for that t squared over h, there is also a flat band in this problem. And you can trace the origin of this flat band by some kind of special states, which we call frozen states. It's a linear superposition when dimer populates a plaquette with proper coefficients. And if you choose these coefficients properly, you can see that this hopping Hamiltonian just does not move this dimer at all. So the state is completely immobile, and out of these states you can create a flat, you create this flat band. And so you can even make like many body states out of these frozen states. As long as they are far away from each other, they will be completely immobile. This is the origin of this flat band. In addition to this dimers, we also studied what happens to clusters. And these clusters, you know, you expect that they become very heavy, because in order to move it, you need to hop every dimer inside of this cluster. So if I have, do not know, if I have a cluster like that, you know, where, and I want to move it, I need to first move this dimer and then this dimer, and this is second order in perturbation theory, like it scales like T dimer divided by J. And that's what we found as well. We got a dispersive band of this width. We also looked into like a 3-dimer cluster, and it also becomes even narrower according to perturbative theory expectation. So basically, of slow degrees of starting from dimers and then progressively bigger and bigger clusters. Okay, so this concludes my discussion of the limits. So anyone wants to ask something at this point? So first of all, like as I argued, this is like just emergent property, right? So it's not the property of the full theory. Just in that regime, it's actually a generic property of confining, strongly confined theories, actually gauge theories. I did not try to develop something like that. I'm not sure if it will have any like topologically interesting properties here. Probably not, but no, we just like studied it so far, like at this level, just trying to understand the physics of, yeah. But it's just emergent behavior here, yeah. Anyone else? Any questions? Okay, so then let me then go to the next part, which is kind of pretty important, I think, both conceptually and also technically for us. So I told you already before that from it's easy to show that the theory is bosonic. So it's built out of gauge fields and Z2 charge fermions, but it should be bosonic because the fermionic parity of physical states is always +1. And so here I show you how to show it, how to demonstrate it explicitly. So first we break the fermions into Majoranas. And then, you know, I want to get rid of Z2 gauge redundancy. So I want to write, introduce new degrees of freedom, which are gauge invariant. So sigma x operator is gauge invariant on its own. So this is simple, but sigma z is not, and also fermions are not. And that's why I'm doing this, I'm sandwiching this sigma z's with my Rana fermions living on neighboring sites. And, you know, in addition, there are these factors of sigma x, and their role is to ensure that all these operators, which I call x and z, that they commute with each other when they are on the neighboring links. You know, otherwise they won't. So I ended up with Pauli operators which act on links and which are completely Z2 gauge invariant. And this is this operator. This is actually what is my physical Hilbert space. My physical Hilbert space, after eliminating the constraint, is just spin 1/2 degrees of freedom living on links of a square lattice. So I would like to argue here that technically this kind of is somewhat related to what Georgie was telling us yesterday about Jordan-Wigner transformation, but like here the physics is somewhat different. In his case, he started from fermionic model and wanted to rewrite it as some kind of you know, spin model with some constraint. Here we start from a fermionic model plus constraint, and we end up with a spin model without any constraint. So in spin liquids, actually, people usually do the opposite direction. So they start from a spin model and they fractionalize. Here we started from the gauge theory and we want to rewrite it as a spin model. So now using this kind of degrees of freedom, I can rewrite everything. So I won't go into details here, but here are some kind of pictures how I can change or rewrite the hopping, you know, in terms of these x and z operators on the right-hand side here, how I can rewrite the plaquette term in terms of also x and z operators, which becomes like a plaquette times a star. And eventually, if I take all my terms in the Hamiltonian, I end up with something like that. So this is now a completely gauge invariant formulation of my problem, written in terms of spins, spin 1/2 acting on links. This is what I got from the hopping term. So this P I did not write explicitly, but it's some kind of projector which checks the fermionic parity on the two neighboring sites. This is what this is related to the density of fermions. It becomes a star operator. This is a plaquette, which is now a product of plaquette and the star. And this is the electric term. This nothing changed. And so now the advantage is that if I want to study, and that's what we do, numerically, this model, it's much better to study it in this formulation because just let me finish the sentence. So the Gauss law is gone and I work in the physical Hilbert space. This is convenient. Yes? Right, so the global U1 symmetry becomes not on-site symmetry anymore. So it's related to this. So my density of fermions is related, because I have a Gauss law, right? I can relate the fermionic parity to a star operator. And so this model still enjoys U1 global symmetry, but it's now should be written. So my particle number generator is exactly the sum, which is written here. Okay. Yeah, it should commute. Hamiltonian commutes with that. Yes, and yeah, exactly. Okay, it's enough. This was easy. Okay, so then I will move on. So, or are there any questions about this duality stuff? I will now tell you about some numerical Hamiltonian, yeah. Okay, so what we do infinite DMRG. So we put our system on an infinite cylinder and it has a finite circumference. It's our main limitation. Usually we have Ly equals to 4. Sometimes we can go higher than that. And now, you know, we look for the ground state and measure some observables. So as a warm-up, what we did, we looked into this kind of regimes where chemical potential is very negative or very positive, which should give us even and odd Z2 gauge theories with confinement, deconfinement transition. And that's what we kind of find. Usually in the MRG, the characteristic to see like a continuous phase transition, you look into what is called the DMRG correlation length, and this exhibits a peak. And this peak becomes larger and larger as you increase the so-called bond dimension. This is an indication of a continuous phase transition. Also in the odd case, you can see that we see some kind of peak which grows. It's not symmetric anymore, but this is also related to the fact that this phase is here, the confined phase. Then what we did some kind of scans. You know, you fix some parameters, magnetic term, hopping, and you just study what happens as you change the fermionic population by changing the chemical potential. And also vertically, what we do, we increase the electric term, which has a tendency to confine our Z2 gauge fields. And so what we get is, like was expected, there is this even regime where there are no fermions, there is odd regime where everything is completely filled. And within these regimes, we have the with topological entanglement entropy, that we increase confined phase. So everything works. But the most interesting part is, of course, in between. So you see there is this kind of wedge here, where we have finite density of fermions, and there it runs, so they can hop, and this is the most challenging part. And so let me kind of show you now. I think hopefully the most robust. It's a tricky regime to study it numerically, but let me show you. I think the most robust numerical results which we found so far. This is set j equals to 0. Or even like, I think if you put negative j, it would also work. So basically, I want to have Dirac semi-metal. I want to have when this electric coupling is small. So what happens if electric coupling becomes large is, as I told you, you end up with these dimers, right? So this is my degrees of freedom, the shortest dimers. And now, in addition to this hopping, which I already discussed, these dimers also repel each other. So second order perturbation theory tells you that they want to be far away from each other. There is a next nearest neighbor repulsion between dimers. And yeah, so what our numerics shows at half filling, that this induced next nearest neighbor repulsion stabilize some kind of strongly correlated Mott phase. So we have this kind of staggered phase where we have, you know, dimers living on this on these links, these vertical links, and no dimers here. You know, this necessarily breaks translational symmetry of the problem. So the phase which we end up here is confined phase of the Z2 gauge theory with broken but broken translational symmetry. We also, this is a result for Ly equals to 8, actually. And we also looked into the Mott gap. And by perturbation theory, you know that if there is this gap, it should be of this emergent T squared over H scale. And that's also what we see numerically. So this kind of brings us to, this numerical observation brings us to the following kind of two corners of the half field case. Right, so on one side we have this Mott phase, which is confined and which breaks translational symmetry. On the other side, we have a Dirac semi-metal with deconfined Z2 gauge fields, which is translationally invariant state. So now the question is how these two phases go, like what is the transition, right, between them? And that we studied two diagnostics. So one of them is the DMRG correlation length. And another one is some kind of flux susceptibility. So you take Z2 flux and you measure it and you compute the derivative with respect to your tuning parameter, which is the electric coupling here. And so what you see is that statistics exhibit a peak, right? Somehow the correlation lengths exhibit a peak which grows as a function of bond dimension, and also the flux susceptibility exhibits a peak. So should be careful with this, of course, because this result is for Ly equals to 4 infinite cylinder. But it's an indication that maybe the transition between this is and not and just one transition actually. So it's possible here that we have a exotic quantum criticality where the confinement and translational symmetry breaking happens simultaneously. And cannot tell you more beyond that. So we started to think how to understand this transition by embedding it into some kind of U1 gauge theory. But for now, I would just indication from numerics. And we are kind of trying to crank up Ly to see if it survives. So it's work in progress somehow. But if it survives, it's an interesting transition, I think. Okay, so let me finish with some kind of outlook. I will tell you some kind of which I think is interesting. And one of them is actually this is what got me started on that. I have some interest in P-wave superfluidity. What kind of fascinated me is that this Z2 field attracts particles. So in contrast to U1 gauge field, it mediates a glue to form P-wave superfluidity. And so it would be nice to understand what kind of superfluid is formed and study its nature precisely in the regime where we have finite Fermi surface of fermions. Also, it's interesting to understand what happens at the edge, especially the role of fermion parity. I told you that the fermion parity is gauged here, so it's not a global symmetry of the problem. So it's a, but if you it's more subtle because there the gauge symmetry survives as a global symmetry, and so to understand the role of this symmetry for the edge physics. Also, in this strongly coupled regime where this H coupling is very large, I told you that everything becomes a physics of these dimers, and everything becomes very, very slow, right? Because it's like this T squared over H effect. So thermalization becomes slow. We can also expect that out of these frozen states, which I told you about, maybe we can form quantum scars. So there are interesting questions about that as well. And finally, in order to understand this problem better, it would be nice to find different ways how to attack it numerically. So far we did exact diagonalization, the MRG, but maybe quantum Monte Carlo is possible if somebody very smart, have good ideas, two-dimensional tensor networks or digital simulations. So if anyone has some ideas how to on this gauge theory, I'll be happy to. Yeah, so that's it, I think. Thank you very much. Right. I think so. So at half filling, you can use leap theorem, right? Somehow to understand that. So in the regime where flipping plaquettes is very cheap or like cost nothing, then you would know, for example, on a, so first of all, you're right. This model can be defined on any lattice you want. So we just took square lattice because we thought it's simplest, but yeah, like. But yeah, then, for example, if you want to understand structure of the fermionic band structure in that regime, you can just use leap theorem. On a honeycomb lattice, it will tell you that the background flux is 0, and you would get like usual, like graphene, like Diracs. Yeah. He wants you to use a microphone, I think. Dynamics, yeah, yeah. Okay, so let me first what I mean by they cannot hop perpendicular. So imagine I have a dimer here, and I'm doing second order perturbation theory, right? So I have T and J. These are much smaller than H and mu. So I'm in this regime. So what I'm saying is, if I would want to hop this dimer upwards, then I would need to hop this fermion here and this fermion here, and then I would end up with a state which is which looks like that. And this is out of my, since I'm doing degenerate perturbation theory, this is not a valid state. I need to come back to the same state which I started with to the same, you know, length of the string. And so what my claim is that the dimer, the hopping of the diamond vertically is a process of T to the 4th divided by H cube. So it's just very suppressed, right? Somehow, that's what I mean.
More questions? Okay, then we thank again the speaker.